Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. The topic of this video is greedy algorithms and their relationship to dynamic programming. In the last video, we had a look at the whole allocation problem and we established that it had optimal substructure of subproblems, which meant we could solve it using dynamic programming. In this video we are going to solve it with a different strategy, which is using a greedy algorithm. What's the story of greedy algorithms and how are they related to dynamic programming? Well, if we look at what we did when we expressed the optimal solution from the dynamic programming perspective, we said, okay, we have a list of possible activities in here, and for each of them, call it AI, it might belong to the optimal solution. I don't know, but if it did belong to the optimal solution, then the optimal solution would have the following shape. AI and some other stuff that's some optimal solution for a smaller problem, and also some other stuff which is more optimal solution to some other subproblem, and so on. And then I say, well, I don't know which of these activities is part of the optimal solution, but at least one of them is going to be. So for that one, the optimal solution has this shape. And now let me consider all the recursive stuff and see how much it comes out to. And then I choose the best among all these attempts, which were all made hypothetically, assuming that that particular activity was part of the optimal solution. Now, the greedy strategy is rather different. Instead of saying, I'll hedge my bets and everything could possibly be an optimal solution, in the optimal solution, I don't know. Well, in the greedy strategy, you're much more bold and assertive, and you say, I know, my hunch is that this activity will be part of the optimal solution. And I forget about all the rest. Let me just go on with my assumption that this is the optimal solution. And then the optimal solution will be form of this, plus some optimal solution to the rest. And for the rest, I can also tell you that this activity will be part of the optimal solution. And so the greed is basically saying, I will choose the first element of the optimal solution based on what I see right now, because it looks the best now, and I bet you this is in the optimal solution. Now, of course, if you use the greedy strategy, you do a lot less work than you did in the dynamic programming case, and you will end up with typically a lower computational complexity. However, you had better be right when you have this hunch that the thing you select was in the optimal solution. So with dynamic programming, although you did more work, you actually checked essentially everything. And so you're guaranteed to find the optimal solution. With the greedy algorithm, you must necessarily prove before you engage in the work that the strategy you use, the greedy strategy you use for picking your first element of the solution, actually pick something that is going to lead you to the optimal solution eventually, rather than being stuck in a local optimum that is not the global optimum for the whole problem. So while the greedy algorithm lets you do less computation, it requires you more thought, because you have to develop proof that your greedy strategy actually works. If you fail to do that, you might be led by the algorithm to something that is a solution, but may not be the optimal one that solves the whole problem as best. As usual, all this blah blah will make a lot more sense if we apply it to a specific example. So let's revisit the whole allocation problem and solve it using the greedy strategy. All right, so déjà vu. This is the problem that we tackled earlier with dynamic programming, allocating the activities to the sports hall. We are now turning the chapter here, page 57. The next thing after dynamic programming is called greedy algorithms. What's a greedy algorithm? Greed sounds like something bad. In this context, it's something nice. It's nice because it allows me to save some unnecessary work. So with dynamic programming, I said, okay, if activity 6 were in the optimal solution, then the optimal solution overall would be 6 plus the optimal solution for this plus the optimal solution for that. However, I don't know if 6 is in the optimal solution, so I have to repeat this business for every activity there is, and for every one of them I have to do this consideration. And so I have this big max over all the activities. The greedy strategy is to say, okay, one of them is going to be the optimal solution, and I have a hunch it's going to be this one, 6. So let me just take 6 and forget about all the rest. That's greedy in the sense that 6 looked to me at the time as the best thing I could do going towards my goal. Now, it should be intuitive that this doesn't always work. And so we have to be careful about defining the circumstances in which it works. However, when it does work, and when I have developed a proof that it will work, then it's actually much better to just select 6, as opposed to saying, let me try over all of these ones, which is the one that gives me the best result. Because I just take 1 at each step, and what I'm left with is something that has its own optimal solution. And if I combine the previous greedy choice with the optimal solution for the remaining sub-problem, I get an optimal solution for the original problem. If all these things are verified, then greedy is an excellent strategy that will cost me a lot less than solving it with dynamic programming. So the problem here is to decide what would be the greedy way to pick the activity that would then actually work. What is the best looking activity for filling in as many activities as there are? Well, I could say, well, if I take 6, is not as good as taking, for example, 3, because 3 gives me more space for other things later. So let me just take the earliest starting activity, because that's the one that I'm not wasting any space behind it. Now, if you look at this particular case, it is true that 1 would be a member of an optimal solution. I will reveal that the optimal solution consists of 4 activities, and so we've already found several instances of 4 non-overlapping activities, such as these ones, for example. So 1 is included in at least one optimal solution, and so it would be a good choice. However, we can make some counterexamples where this doesn't work. So, for example, if we consider let's pretend that we are here. If I take the earliest starting activity between those 3, then it would be this one. But if I hadn't chosen that, but this one, I could have then also chosen this one. So picking the earliest starting activity works in some cases, but not all cases. So that's not so good. So how about instead deciding that I will take the shortest possible activity, because that looks like it might leave more space for other things. So here the shortest activity would be 2, and it would let me take 3, or 3 would also be equally shortest, and it would also work, and it would exclude 4. But we can also make a counterexample where this doesn't work. For example, this 6 here positioned in this way. This 3, I want to have it span like that. Okay, so the shortest activity here is 3, but if I pick that, I'm prevented from taking 4 and 5, which would have been a better solution. So also this one is not a good idea. So if I become more and more elaborate in my attempts at finding the best, I would say, let's pick the activity with fewest overlaps, because fewest overlaps would exclude 3 because it has 2 overlaps instead of these ones that have 1. And this is a good try, you'd be hard-pressed to find a counterexample to that. And I don't have one here. Why don't you, since we are out of time, why don't you think of a counterexample for the problem where you select the one with fewest overlaps, and you want one where that doesn't lead you to the optimal solution. And we'll take it from there next time. So we were dealing with the whole allocation problem where the sports center wanted to allocate activities to the hall in a way that maximized the number of activities. We had already solved this problem using dynamic programming. We had built a matrix, and in the top triangle of that matrix, we had filled in each cell by taking the maximum number among all the possible ways of selecting one activity and then taking the ones non-overlapping before and the ones non-overlapping after with the optimal solution to those two sub-intervals. And so clearly, I would have a quadratic cost for the number of cells plus a linear cost within each cell. So this was bounded by big O of n cubed, the dynamic programming solution, which was a lot better than checking all possible alternatives of do I take this activity in, do I not take this activity in, which would have been exponential 2 to the n in the number of activities. We are now solving the same problem again with a greedy algorithm, where the idea of the greedy algorithm is to say, I'm just going to not try all possible alternatives, but say, with my great insight, I can see that this solution is going to be, this activity is going to be better than the others for some metric, and I am going to select this one, ignore the rest. And so we were trying to think of a heuristic that would make one activity the best of the available ones, because on the face of it, they all look the same. So you could say, okay, we said, what about picking the one that starts earliest, because that might leave more space for others. And we said that looks like a good idea. However, we have a counterexample where this doesn't work. And then we said, what about taking the shortest, because that also leaves more space. Now, that sounds like a good idea, and it worked in the previous example, but we came up with another counterexample where it didn't work. And then we said, that's the thing we said when we stopped. We could select the one that has the smallest number of overlaps with other things, because that would have made the last counterexample actually work. And I said, it's hard to find a case in which this heuristic doesn't work, but there are cases where it doesn't work, and I challenged you to find one. Did anybody find a case where that didn't work? So I'll show you one. It's quite elaborate. Nobody raised their hand, but I'll show you one. So what do I do? Stretch this out a bit. Like this. I'm cheating because I'm putting them where they're not supposed to go, but just for the purpose of illustration. And I need to have some more, so I'll put this one here. This one here. Make it a little short. This one here. And this one here. And they should all be on boundaries, so but I'm also cheating there, but just not, so as not to take infinite time for this counterexample. So this one, how many overlaps does A have? Well, it overlaps with this, so that's 3. This one also overlaps with this, and this, but also this, so this one has 4. This one overlaps with this and this. The other one has 4 and 3, so the one with fewest overlaps is 1. But if I take this one, because it's the one with fewest overlaps, then I'm excluding this one, and so all that remains is to take 1 out of all these, and 1 out of all these, and so the maximum I will reach is 3, whereas it's clear that there is a solution with 4. that I'm now ignoring. So even this other, apparently more clever heuristic of taking the activity with fewest overlaps doesn't work. And so I'm saying, what about all these shots in the dark? There is actually a solution, a heuristic that works, which is to take the activity that finishes before the others. And say, well, now that you've shown me all these things that look like clever ideas when you said them, but then didn't work, how am I going to believe you that this one actually works? And you shouldn't believe it. You should actually develop a proof that it works. This is the trouble with the greedy algorithm. Compared to a dynamic programming approach, if you can attempt both a dynamic programming approach and a greedy approach to solving a problem, with the greedy approach, you will do a lot less work. But it may not work. It may lead you into something that's a local best, but not the global best. And so to make sure that the greedy algorithm works, you have to develop a proof that when you pick your choice, with your greedy choice, with your heuristic, you're actually taking something that is definitely part of an optimal solution. And that if you combine that with the optimal solution to what remains, you get an optimal solution for the global problem. So that's extra work you have to do before you write your program if you use the greedy strategy. So that's a trade-off. So we're going to think about this. Let's consider A. So I got ignore the rest, and let's just talk about this A, these blue things, A and B. So A, my definition of A is that is the activity that finishes earliest. So no activity finishes before this time A2, which is the finishing time of A. And then let's assume for a proof by contradiction that A is not part of the optimal solution. So there's going to be some optimal solution, and within the optimal solution, let's find the earliest finishing activity within the optimal solution. I call that B. So B is the earliest finishing activity in the optimal solution. And how can A and B be positioned relative to each other? Well, there's a number of combinations. I mean, they could be here, 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 but also B could be bigger or smaller than this. B could be like this, could be like this, whatever. So which ones of these combinations are actually possible? So my constraints were that A is the earliest finishing activity. So this point here, B2, cannot come before this one. So B2 has to be on this side of A2. Still, the region is partitioned for B1 into 3 places. So B1 could be this side of A2, between A1 and A2, or before A1. If B1 were before A1, what would I have? It's compatible with my hypothesis that A is the earliest finishing activity because B finishes after that. However, if B is by definition part of an optimal solution, it means there's nothing overlapping B in the optimal solution. But this also means I could replace B with A, and it would still, A would not conflict with anything in the optimal solution because having excluded B, then there's nothing here. And it's just a worthy replacement for B. It just adds an activity which is the same count as B, and I would get a different optimal solution, including all the other things that were in here with B, and instead of B, I have A. So this means A would be part of some optimal solution in that case. If we imagine B1, the start of B, to lie between A1 and A2, as in this configuration, then similarly, it is true that A2 finishes before B2, so A is the earliest finishing activity, and I can again replace B with A in the optimal solution that I have hypothesized exists and has B as its earliest finishing activity. So there exists some other optimal solution which includes A instead of B, so A is still part of an optimal solution. And in the final possible configuration,
for the relative positions of A and B, which is, if I can squeeze them again, where B starts after A has finished. Well, in that case, I am basically contradicting the hypothesis that B was the earliest finishing activity in the optimal solution, because I could build a more optimal solution by taking whatever is in this solution and then adding A, so it gives me one more activity. And so this configuration is not possible under that hypothesis that B was the earliest finishing of the optimal solution, because it wouldn't be the optimal solution anymore, because I can build one with one more activity. So that is an official proof that A is always part of some optimal solution. So I am safe in taking the earliest finishing activity every time. And if I do that, I can solve my original problem just by, well, I messed up the diagram, so I'd have to restore it to actually run the example properly. But I take the earliest finishing activity, I delete all the ones that are overlapping with it, and then I run the same procedure over what remains, which is a contiguous region which is smaller. So I take the earliest finishing activity in this diagram, it would be this one. I take this out, and I take all the things that overlap with it. So I take away this, I take away this, I take away this, take away this, and so on and so forth. This, maybe that's a quicker way of getting rid of that. And what's left, I again look for the earliest finishing activity, which in this case would be this one. And so I'm left with the first one I got, then this one, I delete the ones that are overlapping with that, and so on. And so how much do I pay for this operation? Well, an easy bound is to say that each activity might be scanned in this process here of finding the earliest finishing one. Well, first I have to have sorted them by finishing time, which will cost at most n log n. Then I have one pass for each activity. At each step, I might have to check all the others for overlap. And so a bound would be a quadratic, which is already better than the QB that I had. If I did a slightly tighter analysis, I could see that every activity gets checked for overlap in here. If they're sorted by finishing time, I don't have to check them other than 2 times. Once for this activity, and if it's, well, for it's either deleting in this round or in the next round, I don't have to check them more than 2 times. And so the actual cost of this pass is just linear. And so it's the sorting at the beginning that dominates. And so the whole algorithm can be done in n log n, which is quite an advancement over the dynamic programming strategy. So one thing that's often mentioned in the context of greedy algorithms is a so-called knapsack problem. That's a problem where the knapsack belongs to a thief, and the thief is in a place where there's various items available of various values and various weights, and the thief wishes to fill the knapsack to the maximum possible extent that he can still carry. Or maybe the thief is going to fly Ryanair after the theft, and so is limited to only stealing 10 kilos. And so if he has to steal only 10 kilos, what would he do? Well, the greedy choice would be to take the most valuable item first, which is this 55. You can see if you do that, you can't take anything else. And so the greedy choice is not such a good idea. But maybe it's just because the criterion I've used to inspire my greed was wrong, like we had in the example of the whole allocation. There were many ways to be greedy, and you have to be greedy in the smartest way. So maybe if you had the choice not of the most valuable item per se, but the item with the greatest density of value, so the item for which each kilo of it is worth the most, then you would compute this density like this in pounds per kilos. And so this item over here that I chose was not the most valuable in density, because this one, it weighed less, but it was actually worth more per kilo. So if I took this one, then I would then be able to take this one, and I'd be much happier in total, bringing home 95 pounds within the Ryanair allowance. But even this heuristic of selecting the highest density of value is not guaranteed to work all the time. And we have another counterexample. There's a stray 9 over there. This is a counterexample where even taking the highest density of value does give me the highest value, and the highest density of value will prevent me from taking other things which altogether would have given me a greater value. So this knapsack problem, where you can take or not take items, is not suitable for this greedy solution, at least with these heuristics we have given, because when I take an item, what remains is not a subproblem of the same shape, because now that I have to exclude, what remains is not the original capacity, is some other capacity, and so I have to compare this against not taking that, but taking something else. So this would actually work with a different setting of the problem, where instead of taking or not taking an item, I can take as much of that item as fits. So if these were not gold ingots, but gold dust, then I don't have to take or leave the whole 6 kilos. I can take only 5 kilos of it. Then that heuristic works. But if you have to take or leave the 0-1 knapsack, then that doesn't work. But what would work in this context is dynamic programming, where you try taking or not taking things, and again, there would be exponentially many choices of taking or not taking, but with dynamic programming, you can reduce to some low polynomial number. So here you kind of see the tension and trade-offs between the dynamic programming approach and the greedy approach summarized. And again, with the greedy programming strategy, you will usually have a lower asymptotic cost if it works, but to be sure that it does work, you or someone else cleverer than you has to develop a proof that the optimal choice you're making, the greedy choice you're making, is actually leading to an optimal solution overall.
That's it for this video. Thank you very much for watching. Thank you very much to those of you who are clicking the like button and subscribing to this channel. It's very encouraging and motivating for me, and it encourages YouTube as well to show this material to other people who might also like it.